Hey guys, good morning, good afternoon, and good evening, wherever you are. So today I will go through chapter 2 for process heat transfer. What's the code? NKB20 something something something. Uh, what is it? NKB20303 probably. Anyway. So chapter 2 is about conduction heat transfer. So from chapter 1 we know that we will cover conduction, convection and radiation, and the last chapter is application. So conduction heat transfer, we have three subtopic or three sets of lectures. So here is the first one, and from the book it covers chapter 2 and chapter 3. I mean, for this chapter, chapter 2a. Let's say this is chapter 2a. So, without further ado, let's get started. Oh, anyway, if I get sloppy, then sorry, I guess this is how I roll. Anyway, let's move on. So, conduction heat transfer. Uh, how do I restart this? Put this escape. Yep, that's good. Let's go down. Objective. So there's two objective. Well, it's stated here. I didn't do the notes, so I just read through. So first is you define and describe heat transfer process through conduction, obviously, and you go through a bit of convection here too. So no idea why. We'll get through it. And the second part is determine the rate of heat transfer or heat loss through various geometries and multi-layer system by using Fourier's law. And yeah, Fourier's law, there's a basic for conduction and various geometries. So geometries we'll go through is plane wall, what else? Cylinder, and last part is sphere. So these three things. Alright, so let's go down the other slide. So for this chapter we have, for this part A, we have 37 slides, and those 37s, there's example of on question and so on and so on. Alright, oh, that's the revision. So from chapter 1, heat transfer, there's temperature and heat flow. See, I'm stuttering. So heat flow is the movement of thermal energy, or temperature, the amount of thermal energy available, which is the temperature. You see that what is it? Uh, temperature depends. The energy is mc delta theta. So this is the difference in temperature. So the amount of available energy, the amount of thermal energy available. Oh my goodness. Anyway, we're gonna concentrate on heat flow, the movement of thermal energy. Next slide. Yay. Alright, let's go down. So heat transfer. So heat transfer from hot to cold. So that's the hot surface and that's the cold surface. Draw. That's the cold surface. So heat transfer from hot to cold. So there's a temperature gradient. So this is hot. It transfers to the cold temperature. So here's the guy. Not Shin-chan probably. Yeah. And this guy, Wally. I don't know. So yeah. So heat transfer from hot to cold. So what is heat? Heat is, before, is energy, the movement of thermal energy. So energy transfer from a high energy surface to a cold energy surface. So what is heat transfer? Heat transfer is the rate at which heat flows from hot to cold. Depends on many factors, but there always some flow. Well, factors is determined by what's the thickness, what the uh, K value, what's the H value, and there's a lot of factors we go through during the whole lectures, during the whole heat transfer, actually the whole course. So the shade of the temperature gradient is defined by the condition: hot and cold phase temperatures, thermal conductivity of barrier, heat capacity, and thickness. Oh, I just told this just now, isn't it? Anyway, you can read through. So next is heat conduction. Before is heat transfer, now we go to heat conduction. So what is conduction? Conduction is transfer of heat by the interaction between adjacent molecules of a material, or conduction is transfer of energy from the more energetic particles of substance to the adjacent less energetic ones as a result of interaction between the particles. So what does it mean? I hope it explained here. Yeah, the idea. Let's go down. Go down. So here it is. So this is a hot area and this is a cold area. So hot area receive a lot of energy, so the particle has a lot of vibrates more more vigorously towards the cold particle. How it does it? So yeah, so this part explain it. So in my opinion, in my understanding, is if this particle is heated, it has a lot of energy and it vibrates, and the vibration goes transferred, the vibration energy transferred to the next particles, and the next, and the next, and the next. So over the time, when the heat transfer is stable, the heat flows, the vibration transfer rate, the energy transfer rate will be consistent. Alright, correct me if I'm wrong. So back to heat conduction. So all materials transfer heat by conduction as their component atoms or molecule exchange energy through collision. Hey, did I just say this just now? Alright, that's good. So conduction can take place in solid, liquid, or gases. So what does it say here for solid? Oop. So solids are the most effective conductors because atoms is fixed position. Yeah, it's solid. The atom stays constantly vibrate and interact with their neighbors. So in hot areas, the atom vibrate more and tend to pass energy to cooler region, resulting in heat flow. It depends the way the atoms are bonded together. So if it's highly bonded, then it can transfer energy faster. You know, that's the the idea. Anyway, let's move on. So yeah, so it says before is solids are the most effective and liquid are less good conductors. Why? The interaction are weaker than in solid, and this makes energy transfer less efficient. Sounds right. And then the next part is gases are very poor conductors of heat. The atoms or molecules are widely separate and interact rarely compared to solids and liquids. So let's make an example. Like if you use what they call it, a bubble jacket. So what's in the bubble? Well, they put feather or down in it, but particularly it traps air in it. So since gases are poorly conductors, so the conduction between your body and the outside temperature or outside atmosphere is poor. So your body lose less heat, particularly if it's cold or windy or raining or snowing out there. Anyway, let's move on to the next part. So there's two types: steady and transient heat transfer. So steady implies no change with time at any point within a medium, while transient is implied with variation with time or time dependent. So conduction, we also will go through the transient, but for these two parts, we'll look at steady state heat transfer. So what is steady state heat transfer? I have no idea. So let's have a look. So the part A is transient heat transfer. So Q, which is the heat flow, is not equal to Q1. So Q1 is at 2 p.m. and Q2 is at 5 p.m. So the rate of heat flow is not similar, because here is 15 and 7, while after a while the temperature drops to 12 and 5. So the rate of heat transfer is not same or not consistent. For steady state, the Q1 and Q2 is similar, which means the rate of heat flow. So that's we call a steady state. So the amount of energy transferred is constant. In real life, transient is more prevalent. Well, life is unfair, right? Anyway, let's move on. So multi-dimensional heat transfer. So heat can be transferred in 3-dimensional, 2-dimensional, or 1-dimensional. So in most cases, in real life, heat transfer through a medium is 3-dimensional. However, some problems can be classified as 2 or 1-dimensional. So let's have a look. So 1-dimensional. So let's say for a house with a glass panel. So for 1-dimensional, the primary direction of the heat transfer is outwards the house. So because of the glass also have thickness, so heat also can be transferred upwards at the side of the glass panel. Let's say here also, and here also, and here also, and here also, everywhere. But based on this 1-dimensional, we only consider the heat flow through the one side of the wall of the glass panel. Anyway, then for 2-dimensional, so that's rectangular bar or rectangular box. So heat flow through one side and the other side and goes out through the other side. Well, if it's 3-dimensional, then you can consider it goes through that side and that side too, and this side and that side. Anyway, so that's 2-dimensional. Alright, so next we go to Fourier's law. Alright, now let's look at Fourier's law, and this is for 1-dimensional heat conduction. So it stated that Q over A, which is the heat transfer per unit area, is proportional to the temperature gradient dt over dx. So it says here Q over A is proportional to the temperature gradient, which is dt over dx. So it says here, and so Q over A equal to is proportional. Proportional should be, let me write this first. So Q over A is proportional to dt over dx. So why is minus k is there? Because it's equal, so you need to add a constant, and this constant is called material thermal conductivity, which is labeled by K. Alright, so Q over A equal to minus K dt over dx. Why is minus? Well, we got that later. Oops, back, and there you are. So since we want Q, so the A goes up there, So Q equal to minus Ka dt over dx. So that's Fourier's law. And no, that's not Fourier's law. That's a interpretation from Fourier's law. So Q, the small q is equal to, is heat flux, which is watt per meter square, and Q is heat transfer rate. So that's what you want. Heat transfer rate is watt. Watts, I think watts is power over time, isn't it? Oh, watt is power. Is I don't know. We'll discuss it later. We know it. So K is thermal conductivity, which that's the symbols. That's the symbol. That's the units. And dt over dx is temperature difference, while dx is distance across section. So which is the cross section? This the cross section. Let me draw first. So dx is this x. Okay, so if that is the what we call it, the window pane, and this is the inside, and this is the outside. Oops, what happened? Back, erase. Yep, let's go back. Alright, slight delay there. Anyway, that's Fourier's law. And know that Fourier's law is a vector relationship. So it's a vector, it's a flow of energy. So therefore negative signs appears in Fourier's law of heat conduction, which means I hope it says here, this is because the rate of transfer vector is specific with a specific direction. So heat is transferred from hot to cold. So the energy flows in the opposite direction of the temperature gradient. Therefore, the rate of heat transfer must always be in opposite direction of the temperature gradient. No idea what it means, but I hope you understand it. But from the way I understand it is because of the hot, well, we know that the hot surface has energy in it, while the cold surface has less energy. So energy transfer from hot to cold. So my negative sign is means the energy transferred from hot to cold. That means the energy lost by the hot area. So energy loss for me is negative. All right. So that's my argument. Anyway, so that's Fourier's law. I hope you can grab it. So you just heat transfer per unit area is proportional to dt over dx. So you can derive the heat transfer rate from the Fourier's law. So that's what it meant for. Next, we look at the K value, which is the thermal conductivity. So thermal conductivity K is a physical property of the material. So it depends on the material. It measures the material's ability to conduct heat. So the bigger the K, the better the ability for it to conduct heat. So heat transfer through that material is better. So it varies from this different material. The SI unit is watt per meter Kelvin. And we should know that Kelvin and Celsius has the same ratio, while Fahrenheit and Rankine has the same ratio, but one let me recall. 1 Kelvin equal to 1.5. 1 Kelvin increase equal to 1.5 or 1.6 Fahrenheit increase. Correct me if I'm wrong. So let's look at thermal conductivity still. So it says here it varies for different materials. So let's look at thermal conductivity of different materials. So silver, copper, glass wool, and air. So silver has the best thermal conductivity, while air has the least thermal conductivity. So like we discussed before, if you're wearing a puffer jacket, so the air is less conductive. So this is what it means. It's like 0.024, while silver and copper is 410. So you can guess, if you go out during the winter, if you're wearing a silver jacket and or a puffer jacket, which one you definitely you freeze faster with silver. From how fast is probably very very quick. Anyway, let's look. So this is a graph for thermal conductivity. So let's zoom it a bit. So oops. So that is let's go down. So that's temperature and thermal conductivity of silver, copper, gold. So over temperature, the thermal conductivity of certain materials does change. Like let's say fused quartz. So after let's say where is this 150 Kelvin, so fused quartz increase thermal conductivity increased drastically. So over 1000 Kelvin, which is about 700 degrees C, the thermal conductivity it conduct heats is a heat conductor. Is a good heat conductor, but not as good as silver and copper. But it does increase drastically. So let's have a look at tungsten. So tungsten decreases over temperature. And what else increase? So stainless steel increases over temperature, while aluminum oxide decreases over temperature, but over 2000 Kelvin it increased slightly. So yeah, just follow the graph if they give you graph. Alright, so next is we look at the steady heat conduction in what I said before, in plane wall, in cylinder, and in sphere. So we're gonna discuss it after this. Alright, so now let's enter the realm of heat conduction. So the first part is plane wall, and we have more, which we have cylinder, and sphere. But now we'll go through plane wall first. Alright. So what does it say here? So heat transfer through a wall is one-dimensional when the temperature of the wall varies in one direction only. So what it says here, this is 20 degrees C. Let me draw. This is 20 degrees C, and the outside is 3 degrees C. And that's a middle point there. So this is the cross section of the wall. So not wall, is it a plane wall? Yeah. So this is the x value, the cross section, and this is 20, the inside. I presume this is the inside of a house, and this is the outside of a house. Presumably this is during the almost winter, in the winter, but it's not yet snowing. Alright, anyway, alright, so move on. So steady heat conduction in plane wall. So we derive from Fourier's law. So if you need to recall Fourier's law, go to the first part. So Q equal to minus Ka dt over dx. So minus is because of the vector, because we're losing heat. So how to find the heat, how to calculate, how to derive this equation. Anyway, so dt over dx goes there, dx goes there, and it's become q times dx, and ka dt minus ka dt. So it's all about integration. It's not about the base, it's about integration here. So because this is dx, you integrate over x, and here dt, you integrate over temperature, and here you integrate over the x, which is the thickness. So x1, x2, t2, t2, x2, x1, t2, t1. So integration rule is 1 dx. You get what? You get x. You get x and x2, x1. All right. So you get that, and x2 minus x1. So this is integration rule, form 5. I think form 5 or form 4. SPM lah. Anyway, so q equal to x2 minus x1 equal to minus ka t2 minus t1. So here it's 1 dt. So the integration rules is also similar to the first part. So x goes down, and so you get q, which is the rate of heat transfer, equal to ka t2 minus t1 minus t2 divided by x2 minus. Why is t1? Because this is minus, so it goes inside here. Boom. So t1 minus t2, just to cancel out the minus. All right. So that's the equation for plane wall. Alright, so you just, if you want to know the Q, the rate of heat transfer, you need to know the K, which is the what we discussed in the K value, and then the area, and the area is not the cross section, it's the area of the wall itself. This section, the wall that I expose, this one, the outside wall and the inside wall. If you just use one, not the cross section. All right, so that's the A, and T1 minus T2 is T1. Which one you use T1? So in this example is Q, heat is transferred from hot to cold. So here is hot, T1 is hot, minus the cooler temperature T2. So I'll minus x2 minus x1. But x2 minus x1, this is equal to, oops, wrong. This is basically the x. So basically the thickness. H-I-C-K. Ness. So the thickness of the wall. Alright. So far so good. Alright. So next, oops, wrong. So next is about so the rate of heat transfer, you get that. So we should go thermal resistance, but we skip that for a while, and we pass the example 1, example 2, and we go to hollow cylindrical wall. Why? Okay, first, why is hollow? So in theory, let's say this is a tube. A tube that flows, what flows in it? A steam, or oil, water. So whatever it is. So the tube means hollow cylindrical tube. So something flows in it, and the outside is the ambient. All right. So same O. So Fourier's law, and then so dt over dr, because we use r here. R is what? What is English for r? Radius. Malay is can't remember. Jajari. All right. Anyway. So r goes there, and so you integrate q over dr. You integrate dr, and here same O, you integrate over t. But for the difference is for cylinder, the A consists of R. So that's R in A. Here, where is it? Yeah, where A, that's R. So you have to put A here. In let's look Oh yeah. Let's look back at the. Let's look back, not back. At here, so A here, there's no R, there's there's no X in A, so that's just because X is here. This is X, and for A there's no X value, so there's a width and length. All right. So that's the difference. And where is it? So because there's R in there, so you have to put R first and then transfer the R's to this R section, because you have to integrate all the R values. So integration rule for 1 over R, okay, dr is ln R. All right. Okay, so that's the rules. Don't tell me why, because that's the rule. I have no idea why it become ln R. Alright, so T is similar, but because of negative, so you change. So in the end, the heat transfer rate for cylindrical column cylindrical column or whatever it is 2 pi KL T1 minus T0 equal ln R0 over R1, because ln R0 minus ln R1, so let me write it, ln R0 minus ln R1 is equal to ln R0 over R1. Alright, so it becomes that. So that's how you deduce for cylindrical heat conduction. And yeah, so that's the rate of heat transfer. Actually, anyway, I'll explain that after we discuss sphere. So let's go down to sphere. Okay, that's sphere. This is sphere. No, this is Sparta. This is sphere. So sphere. So this is still a hollow sphere, not a solid sphere. So there's a gap in the middle. So what's normally used for this? Well, I can't. Well, So what else? Oh, let's say have you seen the oil tanker? The oil tanker that carries LPG. So there's a massive sphere. Massive. So massive. It's just massive. So yeah. So in there's liquefied LNG or LPG. So that's type of sphere. All right. So if you watch a movie Guardian of the Galaxy, so the sphere, they use a sphere to protect the, I don't know what they call it. It's a spherical, so that's a sphere too. So probably that's also a heat conduction process too. Yeah. Anyway, movies aside. All right. So Fourier's law, same O, and dr, since we use radius. So what is area for sphere? So r square. They have r square, so r square goes down there, and there's a problem there. So why is minus? So 1 over r square. So if you integrate 1 over r square, it becomes 1 over minus r. Alright, so that's the rules, because there's a rule for you plus r, I think. You plus r, and then it becomes r. You plus r, you times r, and then you times minus r, I think so. So it becomes this one. Go check, Google it, integration rule. Okay, so it becomes this. So in the end, you get it down there. and it becomes erase. It became this. All right. So it's not hard. Sometimes people do memorize this, but so far is if you remember the Fourier's law and you know how to find the area value, which is SPM level. So, well, I say SPM level, but I keep forgetting on the formula. Anyway, if you know how to derive it, you just have to know, you just have to understand how to derive it, and just remember Fourier's law, and then you derive it and you integrate it properly. You can get the the equation, the formula for specific shape. So that's easy for me, I think. Anyway, so that's the rate of heat transfer. So now we're gonna look at thermal resistance. So let's go back to the plane wall. Where is it? Where is it? Thermal resistance. Oh yeah, there you are. All right. All right. Had to stop for a while just then, but no matter. So let's go back to thermal resistance concept. So the analogy between thermal and electrical resistance concept. So let's look at the electrical resistance first. So let's say we know that, well, this is SPM, V equal to I R, and I equal to V over R. So here for electrical current flow, V also can indicate for heat flow as a temperature. So let's say at 1 and 2, point 1 and 2, V1, which is the voltage, is higher than V2. And why? Because it encounters a resistance, and then at the V2 the voltage drops. So for heat flow is also the same. So heat flows from hot to cold region. So here the heat is higher, and then over a layer of substance, over a layer of, let's say, glass or wire or a wall. So the temperature outside, at the outside, is different, it's cooler. So there's a temperature difference. So temperature and voltage, so that's the analogy. Well, I, which is the, what is it, I, current, is equal to Q, which is the heat flow, and current is uh, well, electron flow, isn't it? So R is the resistance. So resistance for R is relatively similar to resistance for electrical current flow. So oops, let's go back to the top. And so this is for plane wall. So we know that Q equal to T1 minus T2 over R. 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 So within these two, R is what? So we can determine that R is, which is over R. So this area must be R. So this whole thing must be R. So R here is what? X2 minus X1, X2 over K A. So that's R. So it says here, therefore R for wall is change of X over K A. So that's the basis of thermal resistance concept, and that's the thermal resistance for a plane wall. Now let's go down and have a look on cylinder. So what's the R for this. So since Q equal to delta T over R, so R here is R is should be ln R naught over R1 divide by 2 pi k L. So that's the R value, and I bet it's the same. Yep. So that's the R value. So R is the bottom over the top, which because R is 1 over R. So together an R, yeah, is the other way around. I don't know what you call that. And then the last one is for sphere. So for sphere also the same. To get R is 1 over R1, 1 over R naught over 4 pi k. Alright, so there you are. So it's easy to determine R. Okay, I guess, yeah. So we've come to the summary. So what's the summary? Define and describe heat transfer process through conduction. We've covered that. Define and understand the Fourier's law. Differentiate between the terms thermal conductivity and thermal resistance. So thermal conductivity is K and thermal resistance is R. Done that. Determine the rate of heat transfer of loss through various geometries. We've covered plane wall, cylinder, and sphere. So I guess what's left is the exercise question. And the exercise question can be also available in the textbook Heat and Mass Transfer, a Practical Approach by Yunus A. Chengel. So it's a black book now. You can buy it, and 85 ringgit, I think. Alright, so that's for we are done for chapter 2A. So next is chapter 2B. I think I'll do it in a separate video because, yeah. So this is about 44 minutes for a part. So yeah, that's good enough. I'm tired now. Anyway, that's it. Like if you dislike, like if you like, dislike if you dislike, because this video is in YouTube. So, well, support me please. Alright, thank you. See ya.